like a really, really long week, you know. Today, we're gonna continue forward. I mean, originally this was the test scheduled day, but we moved it to the mass day, and I figured we'd want the extra 10 or 15 minutes, especially the first time we're doing one of these, that like, no reason to rush, you know. The test will be there the same next week as it is today, so. The things that we do today, is any of this gonna be on the test?
No.
No, the test is written, it's done. Anything we do today is part of, test 2. Any homework that gets assigned would be due until next Sunday. Sunday's assignments, just the 2-6 and the IBT Delta Math thing is all we're looking for Sunday. Yes, sir?
Do we have to finish those AP questions, or that's like the review?
The AP questions are not an assignment. The right and wrong doesn't matter. It's just kind of like for you to get a feel for like what an AP multiple choice question feels like, because there will be 10 of those on the test. So it's just basically review. They'll be in the same style and covering the same kind of topics. I wrote them, but I wrote them like in the style of something like that. Does that feel good?
Yeah.
Okay. Again, I think it'd be crazy not to do them, but like, I get that we're all busy and sometimes like, I think I got the idea that there's 35 of these things, maybe I don't have to do all 35. Like, I get it. All right. So before I kind of dive into this, we're in test 2, we're going to be transitioning from talking about limits and talking about a new mathematical process called differentiation, or the derivative. It'll be new for everyone, I assume. So the origins of calculus, like a lot of the ideas that we'll talk about, are old, like ancient old, like BC old, but had been collected together and formalized into this new branch of mathematics that we refer to as calculus. That happened in like the 16 or 1700s, like right there at the end. So Isaac Newton did this, or is credited with the creation of this, kind of along the same lines. A German man named Gottfried Leibniz was doing like the same kind of work, and they published around the same time, and it was pretty clear that they did the work independent of one another, that one just didn't crib the other's work. Although Newton took out a campaign and basically discredited Leibniz in the same time period as like a fraud or whatever. But history's kind of shown that there's no way that one of them could have known what the other was doing, and that their work the approach was so different, even though it was like the same idea, they couldn't have done this at the same time. So funny story about Newton. Basically, he's at college, like King's College in England, and there's like a plague, and everybody it's quarantine, you go home, like school's done for a while, and like we had for COVID, right? So he goes back home, and the quarantine's like a year or so, and he comes back and he has calculus all worked out, gravity all worked out, like light all worked out, like comes back and has like, it's like the most productive, year in the history of science to that point, like comes back and has just like unbelievable discoveries, like figured out how all this stuff worked that no one had ever been able to figure out before, has it all figured out, like disappeared, worked by himself in his house, essentially in isolation with nothing but his own thoughts, like no one else bouncing ideas off of him, really pretty, like a pretty impressive accomplishment. calculus, Newton does as a side project, because it's his tool that he needs to describe gravity. So the foundation of what we're going to be talking about here when we talk about, when we introduce the idea of the derivative or this process of differentiation, is really, I'm going to frame this as, what is this, like, what question is this designed to allow us to answer? And the question here that Newton's trying to find out is how fast the falling object is moving at an instant. You know, like, you take something, you put it 10 feet high, you drop it, you time how long it takes, and you can compute an average velocity, just taking the distance traveled divided by the time elapsed. And people have been doing that for thousands of years, you know, calculating an average velocity, like how long it takes, just a rate of how fast something, you know, how much distance is traveling over time. What he was interested in is, like, after the thing is falling 5 feet, how fast is it moving at that instant? And that was something that, like, we had no way of computing, but that's kind of where this idea of the derivative is going to be going. And that's what we're going to be building out here in the first parts of this next unit. So we're going to start with the idea, you know, here. So we start with the idea of a circle, and if we say a line is tangent to a circle, from geometry we said that the line intersects the circle at exactly one point, right? But you remember that? Or at least when I say it, you're like, sounds like something we talked about in geometry, but Mr. Kulik, that was like 2 years ago, and like, I wasn't paying that much attention on that day, it seems like, because I'll believe you though. So the question becomes, well, what does it mean for a line to be tangent to a curve? Well, if you notice that we've drawn this pink line P, and we have this curve here, the line definitely intersects the curve, like in more than one place, right? But if I look only at like some neighborhood surrounding the curve, like I can make that neighborhood arbitrarily as big or small as I like, the line should intersect the curve one time. If I can choose that neighborhood, I should be able to choose a neighborhood where the line intersects the curve just once. Everybody's okay with that idea? All right. So if we want to ask, like, is that line tangent to the curve? We're going to say that, yeah, as long as we can find a neighborhood around that intersection, where that intersection is the only intersection, that feels okay. So if we want to write the equation for that tangent line, what are we going to need? Well, we need the point that it intersects the curve. Well, that's, you know, like, we kind of have to have that to start with. You know, you just read it off the graph or whatever. And then we need the slope. So if I'm going to try to, you know, like, figure out the slope of the curve at that point, like, how exactly are we going to do that? Typically, to calculate a slope, we talk about that with regard to a straight line, right? C is a curve, so like, the slope is probably not constant everywhere on the curve. And we typically need 2 points. Well, if I don't know, like, I have the point where I want to draw the tangent to, but I don't know exactly how to draw that tangent, I need the slope. I can't pull another line off the line that I don't know how to draw. And coming from the curve, the only point on the line I have is this point P. feels like I'm missing some information that I would need to write the equation for my line, because I can't compute the slope for it if I can't draw it first. I can't get the slope from the curve because I don't have 2 points on the line. And what do we do? So this is kind of the insight that Newton had. Says, okay, well, what if we start with like a secant to a circle, right? So a line that intersects the circle twice, goes through it. What I can do is if I take the distance from AB and I like continually shrink that down so that like AB is getting closer and closer together, the line I'm getting is getting closer and closer to a tangent. You guys kind of see that? And what we eventually want to do is take that distance between like these 2 points and see what happens as that distance approaches 0. What does this sound like we're going to be doing? It sounds like a limit, right? And that's exactly the idea. So let's do an exercise now on a specific curve here. So let's say we have some curve, right? And this curve is y equals x squared. And we have some point on the curve. It's the point 1, 1. Right? If I plug 1 in for x, I get 1 for y. And I want to, eventually here, I want to turn this secant line, the blue one, into the tangent line, which we've drawn in as the red one. So let's start with the slope of that secant line. So I have like the slope of PQ. So I have 2 points. I have a point on my curve, which is of the form x comma x squared, right? If y is x squared, and the point is x comma x squared that's on the parabola. And my point P is 1, 1. So if I just do y2 minus y1 over x2 minus x1, I have this, right? Is everybody okay with that? That's just me doing this equation for a slope for this secant line, PQ. So for instance, if I have the point 1, if Q is the point 1.5 comma 2.25.
So are you trying to find where it intersects?
What I'm really trying to figure out is the slope that this tangent line has to have. And again, the way I'm going to do that is I'm going to see what happens if I take the slope of this secant line and I get these points P and Q closer and closer and closer together until essentially that distance is 0, which we can't just plug in, right? I can't do a slope calculation with the same point or a point in itself, because I'm just going to end up with 0 over 0, which is indeterminate, which doesn't really tell us anything, right? Does that feel okay? Okay. So if we do this numerically, as an example, so here's my point for Q. I just fill in, this is like y2, and then this is like x2 and x1. I get 2.5 as my slope. And I could do this again, I could get closer, I could do like 1.1 comma, etc., and just keep numerically going down. But what I want to really do is look at the limit as the point Q approaches the point P. Right? Or in general, the limit as x approaches 1 of x squared minus 1 over x minus 1. So we know from limits, if I do a direct substitution, that's 0 over 0. Can't do anything with that. But if I look at x squared minus 1 over x plus or x minus 1, what can I do? Yeah, I can factor that. The numerator factors. And then we can reduce. And now I can do a direct substitution. So it looks like the slope of that pink line, that tangent line, at the point 1, 1 is 2. So we'd say like, therefore, the slope of the tangent line to the curve y equals x squared at the point 1, 1 is 2. So that's what we've shown there. So if I then wanted to write the equation for that tangent line, I have the slope, I have the point. We learned how to do this in Algebra 1 at least, if not earlier than that. And there we go. So if I wanted to do that, I'll just use the point slope equation. My recommendation is all the time when we're writing the equation for a tangent line, we use the point slope equation because we're always going to have a point and a slope, which makes it kind of the easiest one to use. So I would just say like y minus 1 equals 2 times x minus 1. That's an equation for a line unless the directions tell you that it wants it in some other form. You could stop there. If you want, you can distribute things through and you get y equals 2x minus 1. And now it's in slope-intercept form, or if you want it, you put everything, put the variables on one side and it's in standard form and blah, 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 blah. So our takeaway here is an average rate of change is just going to be calculated via slope. It's a secant line. It's a slope. The instantaneous rate of change, that's going to be the slope of the tangent line. So that's where we have to use the limit to get that. Or you could look at, you could do that limit tabular, right? You could look at a series of inputs. That's okay too. But that's the big takeaway. Average rate of change, just regular slope. Instantaneous rate of change, slope at a point that requires a limit, or eventually some other tools that we'll build out to do this in a more efficient fashion. But that's the idea. It was okay? You did average rates of change last year in pre-calculus, I think, right? It's a familiar phrase, right? We're adding in this new idea of an instantaneous rate of change now, which would be like, is equivalent to the slope of the curve, or the slope of the tangent line to the curve at some specific point. That's kind of our preliminary. What we're going to do next in the next section is to formalize this process a little bit more. Okay? So that's 2.7. So this is kind of continuing on. So instead of settling for average rates of change or approximating our instantaneous rate of change by looking at a sequence of secant lines where the points are just getting closer and closer together, we're going to develop a system to do this formally. So we're going to do the same process now in general. So let's say I have some point P on some curve y equals f of x. So we're doing this generally, not for specifically y equals x squared, but for any f of x. That's good. If I want to find the equation for the tangent line, I need a slope and a point. So the P is my point. And then I'll take some other line, I guess, why would I do that? All right. So the Q is my point, and the P is the one that's going to be, oh no, I had it right. So the P is my point, and the Q is the one that's going to be changing, that we're going to let get progressively closer and closer and closer. So the slope of PQ is just going to be, you know, like, we have like, oh, come on now. Our like x1, y1, and our x2, y2. Or I guess I labeled them the other way. Our x2, y2, and our x1, y1. So that's all we have here, right? And we see as Q is getting closer and closer to P, the slope of these secant lines is getting closer and closer and closer to the slope of our tangent line, just like we mentioned. So the slope of that tangent line to the curve at some point P is just going to be the limit as x approaches A of f of x minus f of a over x minus a. Or, if we think about it this way, so I have some point here, and I have some other point that's just h further down from it. We can take the same thing where this is like x2 and y2 and x1 and y1, and just look at as the distance goes to 0. Everybody's okay with that? These two do the same thing. Depending on the context, one of them may be easier to use than the other. We'll kind of get a feel for that as we go. Right now, probably you have no feel for which one would be the easier one to use than the other because we're just starting this idea. So let's go and do an example. Yeah, so this is our tool that we're going to use to calculate slopes for tangent lines. So here we want to find the equation of a tangent line to the parabola y equals x squared at the point 1, 1. So let's say we're using this version. So if I'm using this version, my A is 1, and my f of A also is equal to 1. Is everybody okay with that? And the way I'm getting that is just, because my point is 1, 1. So the x coordinate is 1, and the y coordinate is 1. So if I say the limit as x approaches 1 of f of 1 plus h minus f of 1 over h I can say that's the limit. Oh my goodness. H approaches 0. As h approaches 0 of, now, I know f of 1 is 1. How do I do f of 1 plus h? Well, what's the f of x in this situation? It's y equals x squared. So if I plug 1 plus h into x squared, that's going to be f of 1 plus h, right? Questions on what I've done so far? This is usually the hardest part for students to get the hang of at the beginning. It's just like, what are the names of the pieces? Like just getting straight the symbols and like what you're doing. So stop me now and ask some questions before we start simplifying things down. Just making sure we're comfortable with like where we're plugging stuff in and how we're doing stuff. Mia.
Where did you get the square root of usage?
So this right here, y equals x squared, is like my f of x equals x squared. That's my f of x. So f of 1 plus h means I plug 1 plus h into x squared, right?
Where do you get root?
It's a mistake. That's an h. Thank you. Good question. Yeah, definitely not a 1 on the bottom. That's an h. So good on you. Hey.
This isn't necessarily a question, but could you zoom in the screen a little bit?
Sure.
Or I can move up.
No.
Thank you.
Yeah. Better?
Yeah, thank you so much.
Of course. Totally reasonable thing to ask. All right. So let's continue with this limit as long as we're okay so far. So what should we do to evaluate this? Again, if I try a direct substitution here, I'm ending up with 0 over 0. That doesn't help me any. What should I do? Adrian?
Do you like FOIL the 1 plus h?
Absolutely, yeah. Let's FOIL the 1 plus h out. 100% what I want to do, and I'm just going to do that quickly in my head. Does anyone object to me foiling in my head? Right? Just make sure you're not distributing exponents across addition or subtraction. In the math business, we call that the freshman's formula. Or like, x plus y quantity squared is equal to x squared plus y squared. Implying that's a mistake that like freshmen would make. Right, you have to FOIL there. But what we notice is, hey, some good stuff happens here. That plus 1 and minus 1 knock each other out. And if you look at the fraction, what I'm left with is every term in the numerator has an h in it. And there's an h in the denominator. So those can reduce, right? So I'm left with just the limit as h goes to 0, 2 plus h. Now it's direct substitution time. So that's 2. Guys feel good? Okay. So if I want the equation for the tangent line here, I have my m, and I have my p, so I can just say y minus y1 equals m times x minus x1. Or if I want that in slope-intercept form, I can simplify things down. And there we go. again, unless the directions specify, like you can leave your answer in point slope form, that's fine. If you're checking in the back of the book or something, they may write their answer in standard form or slope-intercept form or whatever, like, if the directions don't say it's not wrong, you can just leave it.
I just leave the two.
I mean, well, you could leave it here, right? That's an equation for a line still, and just in point slope form as opposed to slope-intercept form. So just like, what form should I write my equation for the line in? Just depends on the direction. If they don't specify, do whatever you want, right? Let's do the next example. I'm going to use the other version for the slope, just so you can kind of get a feel for how both of them work. Is that okay? So I'm going to do this version here this time. Actually, I think I used the yellow down there below. Let's use blue. Okay? Just so you get a feel for both of them. They're both doing the same thing. Oftentimes, either can be used. In some select situations, like one of them may be much easier to kind of navigate your way through the limit than the other. But they're both doing the exact same thing. You ready to go? So again, Peyton, my A is 3, I zoom that in for you, and my f of A is equal to 1. Just coming from that. It's that minus f of A over x minus A. Oops. I think, right? Let me double check. Yeah. So far, so good. So f of x is three over x, right? And f of a is just 1. So I have that. And you notice if I try a direct substitution here, I'm going to end up with 0 over 0, right? So that's not helpful to me. So what I want to do now is I want to find a way to wriggle my way through this indeterminate limit. What tool might I use here? What'd you say, Alice? Remember something. Make a common denominator? Yeah, so at some point you got to get rid of this complex fraction that's going on here, right? Now, you can make complex or common denominators and like divide the numerator by denominator and stuff. That's okay. It's a lot of extra work. There's a simpler simplification that'll do the same thing. So the way I like to deal with these complex fractions is I'm going to look at all the denominators. So I have x 1 over 1, and then x minus 3 over 1. So I have x, 1, 1 as my 3 denominators. The least common multiple of those 3 denominators, since they're relatively prime, is just going to be x, right? X times 1 times 1. That'll be the least common multiple of them. Or if I was going to make a common denominator, and those are my denominators, the common denominator I make would be x. And I'm going to multiply that to the top and bottom of this fraction. Again, I'm not changing the value of the fraction because I'm doing it to both the top and the bottom. So that x is going to distribute across the numerator. 3 over x times x is just 3. And then x times 1 is just x. And then the denominator, I'm not going to distribute it to each term. I'm just going to write it times the thing. Because eventually what I know is going to happen, what am I going to have to do on this? I have to do some kind of reducing at some point, right? So why bother multiplying the denominator back out if all I'm going to have to do on the next step is to factor it anyways to get into a place where I can reduce it? In general, when we're doing a technique like this, don't ever multiply the denominator out unless you think that there's like reducing that can happen from doing it. But like, there's no fractions in my denominator. I gain nothing by multiplying the x through. I'm just not going to do it. Okay? You see that it's accomplishing the same thing, right? A little bit more compact way. So now we're going to look to reduce. I have 3 minus x, but I have x minus 3 here. That's really close. But they can't reduce the way they're written. What am I going to have to do here? To get it into a place where I can reduce it, what factoring can I do to this? What if I so the sign on x here is negative, but down here it's positive. The sign on the 3 up here is positive, but down here it's negative. So what should I factor out?
-1.
A -1, yeah. So if I take a -1 out of the numerator, I'd have that, right? Now I move the pieces around so that it looks the same as the denominator. We okay with what I did there though? You guys see the algebra that happened? I paused for a moment to let you guys look at it and think about it for just a second. But those two now can reduce, and that has now cleared my indeterminate hurdle because I'm left with -1 over x. And now I can direct sub that. And there we go. Does everybody feel okay? Peyton?
You may have already said this, but how do you know when you use which formula? Like the f times a plus b versus the f x minus x?
So at this point, you don't have any clue as to like when one would be better than the other.
Okay.
In most cases, it won't matter which one you use. If you get to a limit and you're like, I just don't know what to do to try to resolve this indeterminate form, and you can't make any headway, maybe just try the other one. Because there will be occasions where like one of them is more usable, user-friendly than the other, but in most cases that you guys encounter, it will not matter.
Okay.
So again, like most of the time, it doesn't matter which version you use. In the case where it does, and you try one and you just get to a limit, you're like, I don't know what to do with this. Maybe just try the other and see if you can make any headway with that. On occasion, there are some problems where one of them is much easier to handle than the other, because maybe you can do like a factoring, like a sum or difference of cubes on one that you can't do on the other, and it's more obvious what to do, and just. But in general, like it shouldn't matter. You should be able to do it both ways, but sometimes like one way is trickier than the other. So that's our slope, right? So now we can just do y minus y1 equals m times x minus x1. And again, like you could rearrange that to get into slope-intercept if you needed to, or into standard form if you needed to, but like, is it okay if I skip doing that kind of stuff? Okay, like rearranging a linear equation into a different form, right? That's an okay assumption I make that you guys are confident to do that. Again, if it's not, tell me and we can do more, but I don't want to like belabor, like a detail like that if it's not necessary. All right, so we started this story today talking about Newton and wanting to find instantaneous velocity, like the velocity of the ball after it's fallen exactly 5 feet, right? So we know the average velocity is just going to be the displacement minus the start over the time, right? So this is some position h seconds later minus the starting position divided by those h seconds, right? That's going to give you an average velocity. Is that okay? So if I want the instantaneous velocity, well, that's just going to be what happens as that h goes to 0, right? As the distance between the 2 points, the start and the stop really becomes 0. So if I want to look at 5, and I'm looking at h, instantaneous is, like infinitesimally small seconds later, that should be the same. Okay? So same idea, right? We're doing the exact same thing. Suppose a ball is dropped from the upper observation deck of the CN Tower 450 meters above the ground. What is the velocity of the ball after 5 seconds? What don't we have here that we usually have for this kind of a situation? In the previous examples, what was given to us in the problem that's not given to us here? I have a function, right? What function am I supposed to be using? Everybody see that? Okay, so the textbook is assuming that you guys know like your basic equations for motion. I would not make that assumption. I would give it to you on a test or a quiz. So like if the textbook feels like, hey, this feels like there's something missing, like I don't know, like what equation am I supposed to start with? It's because it's assuming you have it. So I don't remember offhand those either, so I'm going to look it up right now as well. So typically for motion, we use S for position, V for velocity, A for acceleration. So our basic position function, if we're just moving in one direction, is S of t equals 4.9 t squared. So if I want the velocity after 5 seconds, that should be the limit as h goes to 0 of s of a plus h minus, well, let's write a is fine, s of 5 plus h minus s of 5 over h.
What's that S?
Position. Position. I don't know why position gets s, to be honest with you, but that's pretty standard. So we just fill in everybody okay with what I did there? Okay. To simplify here, we'll FOIL this out. And again, I'm going to approach this problem as if I have no calculator, although I would be surprised to see anyone asking you to do this kind of a problem without one. Actually, I'll do that. It's 5 squared. Everybody good there? So if I distribute this 4.9 through to this piece, those two guys will cancel each other out, right? This is just me trying to avoid having to get out a calculator to do this. So that leaves me this. Is everybody okay with the sneakiness that I did just to make the mental math easier for myself? We're okay? And then boop, boop, boop. Can reduce my h's. And if I plug in now I can do my direct substitution. Oops. For a second. Everybody feel okay there? We're okay? Questions so far? All right, so that's part A. Part B asks, how fast is the ball traveling when it hits the ground? So here we're given a time. Here we're not. So what I need to do first is I need to solve for t. So after 450 meters, this thing should hit the ground, right? Everybody's okay with that? So t is just going to be, well, I'll write it as plus or minus. Plus or minus 450 divided by 4.9. And we know if it's time, it makes no sense to have negative there. So I'll discard the plus or the minus from the plus or minus. And now that's a decimal, right? You could type that in your calculator and get a decimal. You don't have to hang on to the thing. But again, I'm going to try to approach this problem as if I have no calculator to use, which is maybe an unfair assumption, but hey, that's what we're going to go with. So now I'm going to do the same thing. So I'll just do v of the square root of 450 over 4.9. It's just going to be the limit as h approaches 0 of s of square root 450 over 4.9 plus h minus s of square root 450 over 4.9 all over h. Everybody okay? I did the same thing, right? I just have a gross looking number for time instead of a nice neat 5. I have this gross looking square root, but like, okay, whatever. It's just more writing, but like, doesn't make the problem meaningfully different. So again, I'll plug these through now. So I'm going to have 4.9 times square root 450 over 4.9 plus h squared minus 4.9 times square root 450 over 4.9 squared all over h. So far, so good. I'm starting to see some nice stuff happening now. So like the squared can cancel the square root. And then this 4.9 will cancel that 4.9. So I'm just left with 450 there in in that component. That's nice, although I'm still foiling the other piece out, which yuckarooskies, but like, well, sometimes you can't have it all, right? So I have 4.9 times 450 over 4.9 plus 2 root 450 over 4.9 plus h squared. Oops. 2h square root 450 over 4.9. Again, I just foiled that out. Oh my gosh. Minus 450. Right, we had that minus 450 left over. I forgot to write it down. And just like before, I'm going to distribute that 4.9 into that first term. The 4.9s are going to be left, or cancel, right? What's left is a positive 450 that'll cancel with my negative 450, just like before. So this is all working out like the same way, just a little bit like, you know, the numbers are a little bit more tedious or whatever, but yes, you're welcome. So I have that, right? Is what's left. Everybody agree? And I'll reduce the h's just like I did last time. Boop, boop, boop. And that clears the indeterminate hurdle for me. And if I direct sub, then I'll have just 4.9 times 2 times square root 450 over 4.9 plus 0. So far, so good. And that's good enough, right? I mean, maybe there's a little bit of cleanup I can do, but not much. I mean, I could do this, I guess. But I don't know that that really accomplishes much of anything. But there you go. There's our yucky looking meters per second in an exact answer. This would probably be something you do with a decimal though. Like, to be quite honest with you, I would not have, I don't think anybody would expect you to grind through that with no calculator where no decimals allowed, but that's the gist of it. So, here we go. Definition. The derivative of a function f at a number a is denoted f prime of a is the limit as h approaches 0 of f of a plus h minus f of a all over h. Or the limit as x approaches a of f of x minus f of a over x minus a. So this slope of the tangent line means derivative, which means f prime. They're all synonyms of each other. They're all asking you to do the same thing, namely the limit of that difference quotient. Is that okay? So we say the instantaneous slope of f of x at x equals a is the same thing as the slope of the tangent line of f of x at x equals a, which is the same as the derivative of f at x equals a, which is the same as f prime of a. All that means just 4 different ways of asking you to do the exact same thing. You're like, awesome. I love when I have 10 different ways to describe something, and there'll be some more notation coming at you that also will mean the same thing. Part of mathematics is like the ability to communicate mathematics, so being able to read the notation, know what it's looking for, be able to write in the language of mathematics is an important component for all mathematics courses. I will do my best to highlight these instances where like this all means the same stuff. I'll try to do that as often as I can, because I think it's helpful. All right. Here it asks us to find the derivative of f of x equals yada, yada, yada at the number a. This will be the last thing I do. This will be potentially lengthy, though. So just if you're having a spot on your notes, this is going to be some writing. So I'm going to use the H definition to do that. Sure. You're welcome. Oops. Right, so I have that. It's okay. Just straight to the formula. So that's going to be a plus h squared minus 8a plus h plus 9 minus the quantity a squared minus 8a plus 9 all over h, and uh-oh! I did something wrong. Who sees what's wrong with what I've written here? You don't see it because this is a mistake that I've seen all of you make many times. Yeah, I forgot to write the limit symbol. On your test next class, you have a bunch of limit problems to do, right? You forget to carry that limit symbol through. Am I going to mark down? Yes. If you carry the limit symbol past where you are supposed to, am I going to mark down? Yes. Where does the limit symbol stop being carried to? The direct substitution step. Once you've plugged the x in, the limit is gone. Up until that point, though, the limit carries through after every equal sign. Everybody's okay? This is me warning you. I've seen you guys all do this. It's okay that you do this, but like, gotta break that habit. The limit is part of the problem. Okay. And then yuckarooskies, Mr. Kulik, like that's some gross looking stuff I'm gonna have to do. So we'll FOIL this part out. I get a squared plus 2h plus h squared, and then I have minus 8a minus 8h plus 9, and then minus a squared plus 8a minus 9, all over h. And you're like, woof, this is getting pretty bad. If I look though, I have a bunch of like terms I can combine. So I have a squared and negative a squared. I have negative 8a and positive 8a. I have positive 9 and negative 9. All of those can just cancel each other out. If I look now, notice that every term left contains an h. Let's reduce. Boom, 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 boom. If I get to that point and everything doesn't contain an h, what does that mean? Means you messed up. Means you messed up. It'll always happen. So if I do my direct substitution, 2 plus 0 minus 8, negative 6. Did I mess? Oh my God, I sure did. Pause. Pause. Let me get out a new color. Does anybody see it? What the mistake is? It happened here at this step when I foiled out. That should be 2AH. Right, I foiled out a squared, or a plus h. So this should be 2a. So that should be 2a. So that should be 2a minus 8. Excuse me on that. It's my fault. But I caught it at the end. Like I saw it, and I'm like, that's not what that should happen. That's not what should have happened there. The reason I'm able to look at the end and know that's not what should happen is because there's an easier way to do this that we'll see here shortly. Eventually we kick this limit definition to the curb and be like, see ya, wouldn't want to be ya. I'll look at a whole bunch of host of shortcuts that make this process obsolete. We'll be working on that, finishing this and working on that next time. I'll put on my ordain the homework from these two sections. Don't worry about them until after your test. You know, like, worry about the test for now. Those homeworks will be fine. If it's too much in the next homework set or whatever, if we need a day to catch up, we can find that time. Good luck studying this weekend. If you need me, find me on Monday or Tuesday or whatever. I'll be around, or later today, you know, whatever. Sure thing.